right, right? Move to the to the right, and then what is interesting here is to note the higher consistency of the air observer on the extreme quality picture, right? Here in the first two pictures, you see that the distribution of the opinion score is almost concentrated on one or two opinion score. While when we take a middle way quality, like something like the third picture, the one in the middle, we see a larger dispersion of the opinion score. This again something that after the training process, we observe that the observer are able to mimic. I mean, this conclusion that we are taking at the single level, at the single picture level, we're also drawn in our paper in a much more general analysis. Yeah, but now I said we need the main question of this talk was to analyze the sensitivity of the air observer with respect to particular transformation that we can do to the input signal and so on. Regarding the shallow neural network case, what we did is adding some noise to the feature to the input feature and see how the output of the neural network behave. Regarding still the deep CNN air observer case, that is much more interesting. What we since it take an image, we can do we can play a bit and see what is going to happen. Like what happened if I apply something, I apply a transformation after which a human viewer is not expected to change his opinion. I am quoting expected here because this is clearly an assumption, right? And we will see later. And also, in many scientific papers, we have been seeing people writing, we designed a neural network that should take a 300 by 300 image patch, and no other clarifications is given, no other explanation is given. And we're wondering whether the approach used to reach this 300 by 300 image patch matters during the inference phase. Okay, let's start by the shallow neural network based case. Again, as I said, the robustness was assessed by adding some noise, and the noise was uniform. We add to the features a uniform noise in the range from -1 to +1% of the useful range of the feature. And for each air observer, we simulate 10,000 realization of the noise and evaluate the performance of the robustness of each air observer by considering two metrics, what we call the correct ratio or the accuracy in general. That is basically the out of this 10,000 repetition of the experiment, how many times the air observer didn't change the opinion, how many times his opinion remains similar to the one of the noiseless case. And also the acceptable ratio, it's how many times the air observer changed his opinion by switching by at most one class of quality on the ACR scale. Like we are, in this case, we are not accepting a switch from fair to excellent because these are two classes. So here is the result in the case of the shallow neural network based air observer. See that basically in 93% of the cases, the probability not to change the opinion. Oh, sorry, there is an airplane. Sorry. Sorry, unfortunately, I'm close to the airport.
Go ahead, we can hear you.
Okay, sorry. Okay, thank you. If you can hear me, then I can go. Okay, sorry. I was saying that there is a 93% of probability that the air observer is not going to change his opinion after adding this type of noise, this small noise that we introduced it. And indeed, there is only in only 2% of the cases, the changes, there is a switch of more than more than one classes, right, after adding the noise. I mean, this result in this particular case of the shallow neural network are interesting, but I will say that they could have been somewhat expected because I mean, it is empirically known that shallow neural network or machine learning or the machine learning based simple model are much more robust to to noise than deep CNN and so on. And that's why I think that we have more surprises in the case of deep CNN based air observer. But let us discuss a bit about the experimental setup here. What are the modifications that we assume that are not that a user of and a human observer will be insensitive to? I mean, again, what we do here, we do a couple of modifications. We take the image and we switch from the color space from the RGB color space to the grayscale. We expect that, right? We expect that this sort of modification won't change too much the opinion of an actual observer. The second transformation that we did is to take the image and add a few noise, few enough, a few noise that should not be perceptible by a human viewer again. But here we are talking about the question of distance and how you, but we don't want to go into that to be so precise. In any case, as I said before, we also want to understand how the approach that yield the patch that the neural network take as input matters. And we consider it two different approaches to reach the input patch: resizing the image or simply cropping the central, performing a central crop and give it as input to our air observer. The air observer were trained originally to take a 224 by 224 image patch. And during the training process, we basically use resizing. Now, this experiment were done on a data set with 20,000 images. And to get these 25,000 images, we took 400 good quality images from the ImageNet competition, compressed them with 5 different levels of JPEG compression, reaching 24,000 images, and each level of JPEG compression was labeled with was labeled from 1 to 5, let's say it like this. Now, these are the results. Let us start with let me move this thing here so that you can, okay. Let us start with the RGB to the grayscale. When we move from the RGB to the grayscale and compare the mean opinion score of the air observer of the RGB image to the mean opinion score obtained on the corresponding grayscale image, this is what happened. I mean, the density, the points are dense more around the y=x line as expected, but we cannot, claim that there is no dispersion. There is some dispersion. The correlation is not 0.99, but 0.9. Yeah, this is what happened at the average level, because we are showing here the mean opinion score of the air observer. Now, if someone look at the individual observer level, again, here I am plotting the probability that each of the observer will not change his opinion after switching the image from RGB, from the color space to the grayscale and so on, and also the probability that he will change his opinion by at most 1 quality level. What you see here, these are the results. Again, we are talking about a probability of around 60% not to change the opinion when switching the image from color to grayscale, and 85% of changing by at most 1. The question, an interesting question, will be doing the same experiment, maybe with actual observer, and see what are these probabilities coming from actual observers. Now, this is the most surprising one, where we try to add, as I said before, a not perceptible noise. Here is a Gaussian noise with a variance of with the mean of 0 and variance of 10 to power -3. These are 2 images to give you an example. I mean, personally, I'm not able to distinguish between the image with the noise and the one without the noise if there weren't these labels. But what happened is that the air observer seems to appreciate the noise. When you look at this is the peak here, and the noisy image, the image with small noise, it's almost every time evaluated as the one with better quality. I mean, one could try to explain this fact by this thing by the fact that AI observer has never seen the noise artifact during the training process and so on, but still it remains surprising. Yeah. These are those results at the individual level. We definitely have lower probability in this case of maintaining or of switching by at most one. Fine. The last experiments that we did concerning this robustness, it's compared, this time it's about the input mode, right? And in particular, we ask ourselves, in one side, on what happens if you resize or if you resize the image, the original image to reach a 324 by 324 patch, or simply take the center crop. And then we do the two things and compare the AI MOS. What happened here again is that, okay, there is a correlation, you can accept it. There's still a density around, not this time, not around the y equal x line, but just a bit below the y equal x. I mean, one could say that, okay, the center crop, it's a subset of the image, and mathematically speaking, maybe the overall quality of the resized image could be smaller or equal than the center crop. But still, this needs to be verified, maybe by running this experiment, using the color as a third dimension, as the third dimension, using the color maybe as the dimension of the original image, to see maybe whether an image with larger size are much more larger from the y equal x line and so on. But yeah, it's an experiment that come to my mind just this morning, and yeah, still didn't do it, but I will do that. Yeah. Obviously, this experiment makes sense only if you are working with images that are not very large, right? And it is more or less the case because the 4,000 image that we are talking about are images with size between like 700 and 500. So times 300 or something like this. We are talking about cropping half of the image, or resizing by a factor of 2. Yeah, this is the result at the individual level. Here you see again the probability not to change the opinion when the image is resized rather than crops and so on. I mean, something that I want to add here is, it seems clearly that if there is such a large difference between cropping and resizing, it means that probably the neural network is quite sensitive to the artifacts that are caused by, I mean, when you modify the aspect ratio of the image, somewhat introduce some issues to which the AI observer, the neural network or the AI observer seems to be really sensitive. So yeah, here again are the probability at the individual level. And this is, I mean, these experiments points out some next steps towards improving our AI observers, right? Particular, we could use, okay, the modifications that I discussed before, to as a way to augment, okay, as a data augmentation approach, and generating, doing those modifications, adding them to the training set in this way to constrain the neural network to understand that the AI observer shouldn't be really sensitive to these particular modifications. But still, it remains the question after these experiments, how to reach the input patch. Is it better to resize? Is it better to crop? Or should we use both to inform the neural network somehow that, yeah, resizing yield artifact, but yield some aspect ratio artifact and so on that humans could accept somehow, okay? But yeah, this is one of the questions. And finally, as Enrico said before, one of the activities that we are currently taking on in the context of the JEG group the JEG hybrid group is to basically design a stamp on how to evaluate deep CNN-based video quality metrics. And we wonder whether this certain of the strange behavior that we analyze, that we observed by analyzing our own air observer, could be the case also for some other, for someone else models and so on. This is a general question that we are posing ourselves, and we'll try to investigate. And finally, I mean, it's also normal to ask ourselves whether this thing, there's something like this behavior here, or this one here, or also the dispersions in here. It's not something that is tax related in the sense that we are considering a different tax than most prediction. We are dealing with air observer. Is a problem that comes from the fact that we trained the model yet on much more noisy labels and so on. So yeah, these are the next directions. And this is all for this presentation. Thank you for your attention.
Okay, thank you. So, are there any questions?
I sent the question,
Okay.
and the question is related to the correlation observer that is mentioned in page and at the first time, like, yeah.
Page
This peak.
six,
Okay.
correlation, observer to observer.
Observer to observer. This one then.
This one.
Okay.
Yes, exactly.
So what is the question? Sorry.
My question is that there are two correlations,
Mm-hmm.
broad correlation, AIO observer and observer.
Mm-hmm.
The observer that is to make correlation, right? It is
Mm-hmm.
not clear for me.
Okay. So maybe let's say that, I mean, I will use Loic take the experiment, Enrico take the experiment, okay? And then I compute the correlation between Enrico and Enrico. That is what I call a correlation between observer and observer. And then when I repeat the same experiment with an air observer, I compute also the correlation between that air observer and Loic, or that air observer and Enrico. Is that clear what I mean here? Or...
Another question from me is if this is a distribution test, right? Why is this correlation and not some KL divergence for some other distance distribution?
It's somewhat hard to me to hear the question. I mean, Enrico, please, if you are close to the mic.
Why do you use correlation between distribution and not the KL divergence?
As an example.
Yeah, as an example.
Yeah.
Divergence.
Yeah.
Sure. I mean, yeah, we discussed this possibility, and the point here is, I mean, in any case, you need to compute the correlations, and then you can use the KL divergence as a metric to evaluate the distance between the two histograms. We discussed this possibility, but the only issue that we have with this is that if you want to use the KL divergence in a scientific paper, then you should have a reference, right? What is the value of the KL divergence that is acceptable? So this is the only issue we had with that approach. But yes, we are trying to see how to embed it in the assessment of to complete these experiments.
You're not convinced. You have a value.
No. It's okay. I mean, there are ways of dealing with that. Yeah.
Okay.
It's not a bad answer.
I mean, ideally, one will reach a KL divergence of 0 and say, I am perfect. But if I say the KL divergence here is 0.02, then okay. The problem is the reviewer could say, okay, what is a reference value? It's low, but what is a reference value? But yeah, still we should find a way to figure out some reference value. Maybe by doing an histogram coming from observer, a set of observer and another set of real observer, using that value as a benchmark and comparing the value obtained between the histogram of A observer and an actor observer, but it's still a step to be done.
Can use a correlator, but the loss function of the correlator doesn't have to be the product, right?
Okay.
Some other distance function.
You can use a correlator, but the loss function shouldn't necessarily be a product, but some other function.
Could be, maybe.
Could be.
Okay.
A better fit for our discussion. Anyway.
Anyway, I think we'll think about that. Thank you for the suggestion.
Definitely. Okay. Sorry, I am just sorry. I will have just to leave because of another issue. Maybe if there are other technical questions, Enrico, please, if you can
Yeah,
answer.
sure.
Unfortunately, I will have to leave. So,
No, but thank you.
Okay.
More or less, we're done.
okay.
Yeah. Okay. Thank you.
Thank you. Thank you again for your attention.
Thanks. Bye.
Bye-bye.
So actually, I mean, this more or less wraps the Ejeye presentation as the session. So as I said yesterday, we'll send Margaret an email. Actually, I already sent her, to update the link to the website if everybody agrees. I mean, and basically the content is still there. As I said, it's just mirror for the old website, and there's a kind of new and more updated information. Okay. So I think we're done with the session.
The hybrid.
Yeah. Sorry.
So we
Thank you.
should move on with the presentations. So there is quite a few presentations left for today. So we should be done at least around 6 o'clock. So and we have now 8 presentations. So and that might be a little bit too much, I guess. So one suggestion is we can move the as Nikolai, the Nikolai's Cracovia presentation to Thursday. Then the other Cracovia presentation, and Lucy, do prefer to do it today, right? Yeah, I mean, since you're here and not on Thursday, then maybe it's better to.
So we can split like
Yeah.
into 2 sessions.
And then we have to see how many of the SAM presentation we will manage